Good morning. Here we go again. This video is going to completely end off everything associated with differentiation. As you can see from the heading, it's differentiation from first principles. Okay, I've got somebody reading around the side there, so I hope the noise doesn't affect us too much. All right, now what is this concept about differentiating from first principles? We already know how to differentiate. We can differentiate polynomial functions, trig functions, exponential functions, log functions, and whatnot. Well, how did they end up with those expressions, or those formulae, as we say, to find those derivatives? Well, first principles kind of shows us. This involves the use of limits, and that's why we did limits before. So let me first of all introduce the concept by proving what dy dx really is from first principles. How did we end up with the expressions that we end up with for differentiating, for example, a polynomial function? Well, first principles is the fundamentals behind the scenes. So without further ado, let's go. You can see I have a graph drawn here, and this graph will be y equals to some f of x function. I'm going to identify 2 points in the graph, P and Q. But these 2 points are very, very close together. I'll explain in a little more detail. I'm also going to use this concept of delta x. Delta x written this way, not this delta x. The delta x written with a triangle means a change in x. Delta x written this way means an infinitesimally small change in x. Very, very tiny change in x. Just give me a second here. Yes, an infinitesimally small change in x. So let me define it first here. Delta x represents an infinitesimal, infinitesimally, infinitesimally small change in x. Okay. Why is that definition important? Okay, give me a minute to format some of this stuff. Yes, because I want the difference in x values between p and q to be very small. Now, clearly based on the diagram you're seeing there, that's a big difference between the x value at p and the x value at q. But you have to think of it as if I have magnified that diagram a couple of thousand times. Right? If I were to go back, if I were to actually try to indicate the infinitesimally small change in x, you obviously wouldn't see the details in between that I will be trying to show you. All right. So I've identified 2 points on the curve P and Q that are very close together. And the difference in x values is delta x, which is an infinitesimally small change in x. So if the x value at P is just plain old x, then the coordinates of P are x and f of x. whatever that x value is, you plug it in. If the difference in x values between p and q is delta x, then clearly q being further down the line, the x coordinate here would be x plus that delta x. And can you tell me what the coordinates of q would be before I write it down? Should be x plus delta x, which is the x coordinate. And what will be the y coordinate? And f of x plus delta x. There. So I have both the x and the y coordinates of p and q. And what I'm going to do, I'm going to draw a line. I'm going to give it a different color. I'm going to color code this thing. This first line will be in red. I'm going to draw a line joining the points P and Q. So there. That line passing through both P and Q is called a secant. Give me a minute. Come on, go through there. Yes, that line passing through P and Q is called the secant. PQ. Excuse me, oh my. All right, the line PQ and the line through P and Q is called a secant. And we can actually try to find the gradient of that secant. You would remember that the gradient of a line, once it's passing through two known points, you can find the gradient of that line as y2 minus y1 over x2 minus x1, right? So the gradient of the secant, I'm going to represent it as m subscript secant. Gradient of the secant is equal to, generically, y2 minus y1 over x2 minus x1, which would be y2. I'm going to use q as the x2, y2. So y2 would be f of x plus delta x. y1 will be f of x, so minus f of x, all upon x2 minus x1. x2 would be x plus delta x minus x1, x coordinate at p, which is x. If you tidy that up a little bit more, you get f of x plus delta x minus f of x, all divided by delta x. The x's will cancel out in my denominator, and I'm just left with delta x. Okay, so that expression represents the gradient of the secant. Okay, no big deal. All right, now this part you got to pay very close attention to, because this is going to give you the concept of the derivative, how you differentiate, and it's going to give you that. It's going to make you understand that concept from first principles. Think of P as being a fixed point on the curve, and think of Q as a point that can move. So what I'm going to do, I'm going to let the point Q move along the curve towards P. Visualize that for a moment. The point Q is going to move along the curve towards P. So I'm going to put Q, let's say, here, for example. Q is now here. And by the way, make this thing look proper. Q is now somewhere there. By the way, this distance here was delta x. You'd remember that. From there to there. And then, oops. From there to there. That distance, the difference between the two, the difference in values between the two x values there, that's delta x. Right. Now I'm gonna let Q be here. So what would the secant PQ now looks like? Well, let me draw that secant in a different color. Make it smaller. Make it a hard green. The secant PQ now looks like this. P is fixed. What are you doing? There. The secant PQ now looks like this. Extend this a little further out. Well, that's the secant PQ. Go away. Come back to you. I'm spending a lot of my time editing instead of explaining. All right, so that's the secant PQ. Now, what do you notice about this is the new point Q. Remember, Q is moving along the curve towards P. So this is the new Q. What do you notice about delta X, which is the difference in X values between P and Q? Delta X is now smaller. Delta X is now the distance from there to there, right? Do you see that? I'm going to draw one more secant. I'm going to put Q a little further along the curve. You can clearly see as delta X is getting smaller and smaller. Sorry, you can. All right, I can't move that dot. Yes, as delta X is getting, as Q is moving towards P, delta X is getting smaller and smaller. I want to put Q here. I want to put Q here, somewhere there. And I'm going to draw one more secant. What's a nice color to use here? A rainbowish looking color. Use yellow. Hope it shows up. If Q is now there, the secant now looks like this. So look at what's happening. Right? This is the new change to black. Doesn't matter. Doesn't matter. I'm not gonna spend the time. Looks like I'm trying to spend the time. Right, this is a new position for Q here. So as Q is moving closer and closer to P, delta X is getting smaller and smaller. It looks like it's approaching 0. What does it look like that the secant is approaching? The secant PQ. What does it look like as if it's approaching? I'm going to give you a minute to think about that while I formalize all this into some standard language. As Q approaches P, delta X approaches 0. See, delta X is getting smaller and smaller. And the secant PQ approaches, figured it out? The secant PQ approaches a tangent at P. Well, if the secant PQ approaches a tangent at P, It implies that the gradient of the secant, PQ, approaches the gradient of the tangent. This would imply that the gradient of the secant write properly. The gradient of the secant PQ approaches, I'll use the R to represent approaches, the gradient of the tangent at P. Let's see if I can say that in a slightly different way. When I say as Q approaches P and as delta X approaches 0, that's another way of saying the final value that the gradient of the secant approaches. Right, I should have read back the entire thing. As Q approaches P and as delta X approaches 0, and the secant PQ approaches the tangent at P, this implies that the gradient of the secant PQ approaches the gradient of the tangent at P. I'm going to write that another way. The final value that the gradient of the secant approaches as Q approaches P, which is the same as saying as delta X approaches 0, the final value the gradient of the secant approaches as delta X approaches 0 is the gradient of the tangent at P. All right, well, everything I've written there is in English, standard English. Is there an equivalent mathematical way that I can say the same thing? Is there an equivalent mathematical way that I can say the final value that the gradient of the secant approaches as delta X as Q approaches P or as delta X approaches 0? Well, it wasn't coincidental that the topic that just came before this was limits. Remember what a limit was? A limit was the final value that a function approaches. Final value that a function approaches. So, the final value that the gradient of the secant approaches as delta X approaches 0, the mathematical way to write this is as follows. The limit as delta X approaches 0 of the gradient of the secant is equal to the gradient of the tangent. Is equal to the gradient of the tangent at P. So, that's it in a nutshell right there. Let's formalize that because we did come up with an expression, right? For the gradient of the secant. Here it is right there. F of x plus delta x minus f of x divided by delta x. So I'll rewrite this as the limit as delta x approaches 0 of the expression for the gradient of the secant, f of x plus delta x minus f of x, all upon delta x, is equal to the gradient of the tangent at P. And how do you find the gradient of a tangent line to occur at a point? Come on, I know y'all know. I know you know. That is dy dx. Use the gradient function dy dx. Effectively, that's how we've come up with the gradient function dy dx from first principles. The gradient of the tangent at P is found from the limit as delta x approaches 0. The final value as delta x approaches 0 of the gradient of the secant gives you the gradient of the tangent, which is dy dx. And that's the key right there. I hope y'all appreciate what this means. I mean, I could have just given you this formula and say, here, use it to find all your derivatives from first principles. But I thought it would give you a much better appreciation for how you find derivatives from first principles if I were to actually prove it. There. Concept is very useful. You draw a secant through 2 points that are very close together. Of course, I can't literally or physically draw them close, so very close together that you can't see the details. They're close enough together that the difference between the x values is called delta x, an infinitesimally small change in x. And obviously, to see the details, I have to effectively magnify it quite a bit. So the diagram you're looking at is a magnification of what's going on in reality. And then I'm going to let Q simply approach P. As Q approaches P, delta x approaches 0. As delta x approaches 0, the gradient of that secant becomes the gradient of the tangent. How do you find the gradient of a tangent to curve at a point? dy dx. All right. Now, obviously, they're not going to ask you, obvious to me, but they're not going to ask you to prove, very unlikely, they're going to ask you to prove this. If for some strange reason they ask you, anyway, it's supposedly multiple choice, but just in the event that the CXC gives into all these letters I'm noticing posted by Guyanese authorities and quite a few students. Congratulations, students, on representing us. But if for some strange reason we end up having to write the long paper as well, which would be good, and they do ask you to prove it, well, here's the proof right here. But for all the problems that we're going to work from here on in, we're going to use that as a formula and use it to our advantage. So, without further ado, let's just jump right in. I have a list of the more common ones that they usually ask you to find to differentiate. F of x is equal to, I'll do sine x, and I'll do f of x is cos 2x. And I'll make this first one x squared plus 1. So, let's run through the examples so that at the end of this, we're in good shape and we can differentiate from first principles without issues. All right. Differentiate each of the following from first principles. Okay. And the first one, I like to call the function f of x and not y, because I can use this formula directly with the f of x plus delta x and so on. F of x is equal to x squared plus 1. From past experience, I know students have a strange problem for whatever reason in finding f of x plus delta x. They get confused. And I usually clarify that as follows. If I wanted f of 1, you'd obviously plug in 1 wherever you see x. So that would be 1 squared plus 1. If I wanted f of 6, you would plug in 6 wherever you see x. 6 squared plus 1. If I wanted f of a half, you'd plug in a half wherever you see x. A half squared plus 1. If I wanted f of a, you'd plug in a wherever you see x. A squared plus 1. If I wanted f of a plus b, you'd plug in a plus b wherever you see x. A plus b all squared plus 1. So if I wanted f of x plus delta x, you'll obviously plug in x plus delta x wherever you see x. So that would be x plus delta x all squared plus 1. I hope that clears that up for from past experience. Pretty much every year, there are a couple of students who have an issue with finding the expression for f of x plus delta x. You simply plug in x plus delta x wherever you see x in the function f of x. No different than I've done here. Okay. Let me get rid of this. All right, so clearly f of x plus delta x is equal to x plus delta x all squared plus 1. Okay. By definition, to find dy dx, that's the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. So let me plug in. Dy dx is equal to the limit as delta x approaches 0 of the expression for f of x plus delta x, which is x plus delta x all squared plus 1. Gotta get square brackets around that. Minus the expression for f of x, which is x squared plus 1, all divided by delta x. Now, you would remember from our limits that when you're finding the limit of a function, one of the first things you do, you plug in delta x up front and see what happens. Or plug in whatever, if it is x or theta, whatever the case is. In this case, I'm plugging in for delta x. Wherever I see delta x, I'm plugging in delta x equals 0. So wherever you see delta x, you plug in delta x equals 0. So in the numerator, there where I have delta x, I'll plug in 0 there. So I'll have x plus 0 all squared plus 1 minus into x squared plus 1 all upon 0, which gives me x squared plus 1 minus into x squared plus 1 upon 0. In my numerator, I also have 0 upon 0. I remember whenever we end up with 0 upon 0, we say that is undefined. 0 upon 0 is undefined. And we have to massage the function in some way so that we can re-substitute or delta x equals 0. You will always find that to be the case. So generally speaking, I don't, for the differentiation from first principles, when I plug in directly for f of x plus delta x minus f of x upon delta x, even up here, if you think about it, directly here, if you plug in delta x equals 0, you'll get f of x minus f of x in the numerator, which is 0, and the delta x equals 0 in the denominator as well. So you will always get 0 upon 0 whenever you plug in directly into this formula, if you plug in delta x equals 0. Always, without fail. So the idea will always be to somehow rearrange the function, as I say, massage, quote unquote, the function, in such a way that you can plug in delta x equals 0 without ending up with something undefined, like 0 upon 0. The easiest way to approach that in this case is to expand your brackets with the delta x, with the x plus delta x. So let's see what that's going to give us. Dy dx is equal to the limit as delta x approaches 0 of, if I open that perfect squared, everybody knows how to do that by now, x squared plus 2 times x times delta x plus delta x all squared plus 1 upon minus into x squared plus 1 all upon delta x. This gives me the limit as delta x approaches 0 of, okay, x squared plus 1, the x squared and the plus 1 will go out with this x squared and the plus 1 with the minus in front of the bracket there. What's left over? 2x times delta x plus delta x all squared. By the way, another point that I need to bring up, divided by delta x. This expression here, delta x all squared, you should always write it like that. Don't write it as delta squared x squared. You don't carry in the squared, delta squared x squared. That's not correct notation. Delta x is one quantity on its own. You can't separate the delta from the x. And similarly, like this 2x delta x, somehow students like to multiply this x by this x and get 2 delta x squared. That's wrong as well. That's not permissible. Delta x must stay on its own. If you're multiplying by another delta x, you can refer to that as delta x all squared, like that. So be careful, look out for those things. Don't do that. Okay, this now becomes the limit as delta x approaches 0 of, in my numerator I can factor out a delta x, can't I? Yes, if I factor out a delta x, I will get delta x into, what's left in the brackets? 2x plus delta x upon delta x. Delta x will cancel out with delta x. And now this becomes the limit as delta x approaches 0 of the expression that's left in there, 2x plus delta x. And now I'll substitute delta x equals 0 again. Direct substitution at this point gives me 2x plus 0, which is 2x. So if f of x, maybe I should have dy dx or f prime of x, just to keep the note. I'll leave the first one as it is. Dy dx or f prime of x. The f prime of x notation is a little more meaningful in this case. Not that dy dx is wrong, because f prime as well as dy dx both mean the same thing. So dy dx or f prime of x is 2x in this case, given that f of x or y was x squared plus 1. Now, we always knew that from when we started calculus, right? If you have y is equal to 2x plus 1, you use the function for differentiating a polynomial. Y is equal to ax to the n. And you could easily get your 2x from that. When you differentiate the 1, you get 0. But that if you just give them dy dx is equal to 2x there, guess how much marks you're going to get? Take a wild guess. They're not going to give you any marks for doing that, for just writing down dy dx is 2x. They want to see that you can use the concept of first principles, use the concept of limits, massaging your function in such a way that you can plug back in afterwards and actually get the derivative. So be careful. Don't try this. Don't just write down. What you can do is, as a quick side working, know what you're supposed to end up with. Like, I know if I differentiate x squared plus 1, my result would be 2x. Well, that's exactly what I found using first principles. So that's my answer there. And that's the first one. Yes, some of them are pretty lengthy, but you got to go through it. If they ask for first principles, give them first principles. Okay. Let's try the next one. F of x is equal to x cubed. Yeah, they can get very, very lengthy sometimes. f of x is equal to x cubed, f of x plus delta x. Well, you remember how you get that, right? Wherever you see x in the function, you replace it with x plus delta x. So that would be x plus delta x all cubed. And we know that by definition, dy dx, or f prime of x, I'm going to start referring to it as f prime of x from here, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all divided by delta x, like so. So f prime of x is the limit as delta x approaches 0 of f of x plus delta x, which is x plus delta x all cubed, minus x cubed, which is the f of x, all divided by delta x. Again, you're guaranteed to get 0 upon 0 if you plug in delta x equals 0 directly. So that's not going to solve the problem at this point. The question is, well, how do you solve the problem at this point? F prime of x is equal to the limit as delta x approaches 0 of, well, you got to open up that cube, right? So that will be x cubed. Y'all should know how to do this by heart. Plus 3x squared times delta x plus 3x times delta x all squared plus delta x all cubed. That looks good. Minus the x cubed that's at the end there, all upon delta x. The x cubes will cancel out. F prime of x is equal to the limit as delta x approaches 0. When the x cubes go, what do I have left over? 3x squared delta x plus 3x plus 3x times delta x all squared plus delta x all cubed, all upon delta x. Okay. I can factor out a delta x. In fact, I'll start skipping steps because y'all, the algebra should be tough enough to deal with that. If you think about it, all three terms in the numerator have a delta x. If I factor out that delta x, it's going to cancel the delta x in the denominator. So f prime of x will end up being the limit as delta x approaches 0 of what's left in my brackets if I factor out the delta x from the numerator and cancel it out with the delta x in the denominator. That would be 3x squared plus 3x delta x plus delta x all squared. And now I can plug in delta x equals 0. And everywhere, every term that has a delta x, if I plug in 0 there, I'll get 0 for that term. So this becomes 3x squared. Remember, I'm plugging in delta x as 0 plus 0 plus 0. Or technically, if you want, plus 3 times 0 plus 0 squared. F prime of x is therefore 3x squared, which we knew from our regular differentiation. So when, let me summarize, if f of x is equal to x cubed, then f prime of x is equal to 3x squared. Yay. Not too bad. Hope it's starting to take shape. There. Let's deal with root x. I'll leave some of these for you to do now. Let's deal with root x. Yes. F of x equal root x. F of x is equal to the square root of x. F of x plus delta x is equal to the square root of x plus delta x. Remember, whenever you're finding x plus delta x, everywhere in your expression where you see x, you replace it with x plus delta x. Okay, by definition, we should always use this expression f prime of x is equal to the limit as delta x approaches 0. Yes, the limit as delta x approaches 0 of f of x plus delta x minus f of x all divided by delta x. If I plug in, f prime of x will be the limit as delta x approaches 0 of the root of x plus delta x minus the root of x all divided by delta x. Try plugging in delta x equals 0 at this point, you'll get 0 upon 0. So that's not going to work. Well, how are we going to deal with this one? You should remember from your limits, that's why we did limits first, what you need to do when you see a radical, you rationalize. In this case, we're going to rationalize our numerator. Now, sometimes what I like to do, when that function in there starts to get a little too crowded, complex, not complex, but a little too lengthy, I just pull it out and work on it, simplify it, and then plug it back in instead of dragging the limit around with it all along. So I'm going to try that here. I'm going to say consider the root of x plus delta x minus the root of x all over delta x, which I will rewrite as the root of x plus delta x minus root x upon delta x times the root of x plus delta x plus root x upon the root of x plus delta x plus root x. I'm rationalizing my numerator. And how do we do that? Multiply the first two minus multiply the last two. Remember, the middle terms will always cancel out. So root of x plus delta x times the same root of x plus delta x is x plus delta x. Y'all gotta excuse me for a minute. Okay, I'm back. Yes, root of x plus delta x times root of x plus delta x is just x plus delta x minus, and in the next pair, root x times root x is just x. So that's my numerator. In the denominator, I have delta x hanging out there into the root of x plus delta x plus root x. How does that look? I think it looks good. X minus x will cancel out. And the delta x that's sitting up there alone now will cancel out with the delta x in the bottom. So what's left over? Just 1 over the root of x plus delta x plus root x. Now what do we do with that? Well, we write it back in terms of the limit because we're finding f prime of x. That is now my new expression for this thing I considered, which came out from there, now looks like that. So therefore, f prime of x is equal to the limit, as I'll write both, approaches 0 of the original thing, which was the root of x plus delta x minus root x upon delta x. But this couldn't give me the limit directly because I would have gotten 0 upon 0. So therefore, this gives me the limit as delta x approaches 0 of my new expression, which is 1 upon the root of x plus delta x plus root x. Hey, man. Okay, if I plug in delta x equals 0 here, I will get 1 upon the root of x plus 0 plus root x. You remember, it's delta x I'm plugging in a 0, not x. Delta x is going to 0, which is 1 upon root x plus root x. And everybody knows that 1 mango plus 1 mango is 2 oranges. So that's 2 root x in the bottom there. And that's the derivative. If f of x is equal to root x, then f prime of x is equal to 1 upon 2 root x. We can even check it against our regular derivatives, right? Y is equal to root x, which is x to the half. So it's in the form ax to the n. dy dx is equal to a half x to the power half minus 1, which is minus a half. If you throw the x to the minus a half into the denominator to join the 2, that becomes 1 upon 2x to the half, or 1 upon 2 root x. So, first principles method got us there. Don't forget, when they ask you for first principles, don't give them the standard classical way of differentiating. You're guaranteed to get 0. I would give you 0 minus. 0 minus, just before 0. All right, so that's that one. Let's try a couple more. Get rid of this sideshow. Everybody can do that. Okay. Next one in line. So I've done, let's see. I've done this one. I've done this one. I've done that one. I'll leave the 1 upon root x for you to do. No. I'll do that one. I'll do that one. 1 upon root x. F of x is 1 upon root x. F of x plus delta x will be 1 upon the root of x plus delta x. We know that f prime of x will be the limit as delta x approaches 0 of f of x plus delta x minus f of x all upon delta x, by definition. You should know this by heart by now. Okay. F prime of x, therefore, in my case, will be the limit as delta x approaches 0 of f of x plus delta x, which is 1 upon the root of x plus delta x minus 1 upon root x all upon delta x. Let me make this bracket a little bigger. Okay. All right. What I want to do is to make this entire thing into a single fraction first, before I rationalize. If I indeed have to rationalize, I think I still have to rationalize. So I'll pull it out and work on it. Consider 1 upon the root of x plus delta x minus 1 upon root x all upon delta x, which is equal to, in my numerator, I'll have an LCM of the root of x plus delta x times root x. I'll have root x there minus the root of x plus delta x. I should know that, right? Your algebra should be good enough. And all of that's still divided by delta x. Well, these two join up to become a single denominator. And the expression now becomes root of x minus the root of x plus delta x upon delta x times the root of x plus delta x times root x. Another way we could have thought of that is to multiply both numerator, which is up here. All of this. Multiply both numerator and denominator by root of x plus delta x times root x. You would have ended up exactly there. Exactly here. All right, now we're not finished yet. I'm pretty sure, because even if you substitute delta x equals 0 here, you'll get 0 upon 0. So it looks as if we have to rationalize. Looks as if we have to rationalize the numerator in this case again. So I'm going to multiply top and bottom by the root of x plus the root of x plus delta x upon the root of x plus the root of x plus delta x, like so. Okay, what do we do from here? Multiply across the top. Root x by root x is x minus into root of x plus delta x times root of x plus delta x is just x plus delta x. Don't forget, you got to put it in a bracket like that. Upon, the denominator looks interesting. All upon, I'll have delta x times the root of x plus delta x times root x all into, because remember I'm multiplying these two, into this piece, which is root x plus the root of x plus delta x, like so. If I push that minus sign inside my numerator, yeah, I'm gonna let you figure this out to yourself. I'm not writing an extra step. X minus x will cancel out. What's left on top? Minus delta x. Well, the delta x will cancel out with that delta x, because remember, everything on the bottom is multiplication times this bracket, of course, at the end here, which is multiplication as well. So what's left in my numerator is minus 1, and what's left in my denominator is root of x plus delta x times root of x into root of x plus root of x plus delta x. Mercy. And therefore f prime of x has to be equal to the limit as delta x approaches 0 of what I have left there, minus 1 all upon the root of x plus delta x times root x into the root of x plus the root of x plus delta x. Now, hopefully when I plug in delta x equals 0 into this, I wouldn't get 0 upon 0, but I can't get 0 upon 0. Because certainly in my numerator, let me see, f prime of x is equal to, I'm finding the limit now, so minus 1 upon root of x plus delta x is like root of x plus 0. Everywhere I see delta x, I'm plugging in 0 times root x into root x plus root of x plus 0, which is minus 1 upon, okay, what do I have? Root of x plus 0 is just root x. Root x times root x out here is x. So those two will give me x. And on the inside, I have root x plus root x, which is 2 root x. F prime of x is therefore minus 1 upon minus 1 upon 2 times x times root x. Let's see. X times 2 times x to the half. X times x to the half is x to the 3 halves, which is 2x to the 3 halves, or 2 times the root of x cubed. Yeah, that's how I'm going to write it. Minus 1 upon 2 times the root of x cubed. You get that if f of x was x cubed, was what? Was 1 upon root x. Would regular differentiation give me the same thing? Y'all should double check. Every time you do one of these, just run through a quick regular differentiation, classical differentiation technique, and see if you get the same thing. I'm pretty sure you will. Well, once you apply your limits and your algebra is correct and so on. I'm going to do 2 more of these. I'm going to do this guy. Oops. I'm going to do this one. And I'm going to do sin x. 21. Ooh, it is an hour already. Maybe I should stop this video here and start another one. I don't want my videos to be more than an hour long for any one of them. Yeah, let me stop this one here and I'll simply start another one where I simply continue working more problems. I might get to work out more problems in that way. All right, no worksheet at the end of this one. Y'all happy, huh? All right, that's it for this one.